concept, that is physics. Here you see I am talking about rigid body. Rigid body. So what happens here, that say this is a rigid body, some rigid body, and it is rotating about z axis. It is rotating about z axis, and this is the origin. So this is your x axis and this is your y axis, rigid body. Now we consider point P here, and let us take this surface. We are taking this point P here. That means this section is the section which is perpendicular to the z axis. So we can redraw like this, that is your z, and this is your x, and this is your y. So here this is the plane, it's point P. Your angular velocity is in z direction. That means this is rotating about the z axis. Here this is rotating about the z axis. Now let us take this from here, from the axis C, this is O, and this is your position vector R. So here it is moving with angular velocity. Now concept, what is the concept? Your angular velocity is a vector quantity, So here we are going to find angular velocity. So here omega v vector, that is equal to omega vector cross r vector. This is your r vector from the origin, and so now let us see v vector. And one more important thing is that each particle of this body is rotating with omega velocity, each particle. That is, the concept is that each particle is rotating with omega. That means we can consider this whole body, the body is rotating with omega, that is angular velocity. This is the concept here. Now v, it is equal to omega cross r. So your r, this is the position vector, so this will be omega vector cross your r vector is OC vector plus OP vector. This will be OC vector plus OP vector. Now here you see that this v vector will be omega vector cross OC vector plus omega vector cross OP vector. So what do we find here is that your OC and omega, they are in the z axis. That means we know that in cross product in cross product, we know that in cross product it is AB sine theta. So here your theta is 0, so this is 0. Now you are left with only V vector, that is equal to omega vector cross OP vector. So what is this? Sorry, CP. This is CP. CP vector. CP vector. This is CP vector. Omega cross CP vector. So what is this CP vector? So this CP vector, it is the perpendicular component of R vector. So V is equal to omega R perpendicular. This is your R perpendicular. This is your magnitude. So the magnitude is V dot R perpendicular, that is the perpendicular of this. So this is your magnitude. This is what is this? This is your magnitude. So the concept here is that each particle of this body is moving with angular velocity. That means the direction of angular velocity does not changes. Direction of angular velocity does not change. Does not change. So this is the concept. That means each particle of the body is rotating with angular velocity. Each particle, so the body is rotating with angular velocity. Now here V velocity, that is equal to omega cross R, where R is the position vector. So V vector is equal to this. Now this is 0 because your omega is in z direction. I have taken omega in z direction. So omega is in z direction, and this CP vector, it is the perpendicular component of this. So it is the perpendicular component of this. So here your omega and this R, they are perpendicular, so sine 90 is 1. So this value is this is the magnitude. So what I want to tell you that that is the, here you see that, want to tell you the concept, that is the direction of V velocity. Direction. What is the direction? Direction. This is the concept. So what your omega is along the z axis. This is omega is along the z axis. So here cross, that is omega cross, this is omega. So omega cross R, this is R. This is omega cross R. Your R is the position vector. So omega cross R, see, omega cross R, because the main concept here is that in cross you will always take the screw rule, that is the screw rule, omega cross R, see, omega cross R. So omega cross R, and at the same time the direction of V must be perpendicular to the plane containing omega and R. So perpendicular plane containing omega and R. So if you take the screw rule, there is omega R. That means you are tightening the screw, so the direction of the velocity will be this. This will be your direction of the velocity, which is tangent to the tangent at point P. So this is the direction of the V velocity. So the concept here is that how will you determine the direction of V? So you take omega cross, because it is a cross product, so omega cross R, here omega cross R. This is the screw rule. That means you are tightening the screw. That means its direction will be into the this plane of the paper, and the weave must be perpendicular to the plane containing omega and r. It must be perpendicular to the plane containing omega and r. So there are 4 concepts. So what is the concept? That each particle is rotating with omega, and second, the body is therefore we can consider the body is rotating with omega, and direction of omega, it angular velocity does not change. It does not change. It will be in z direction. So in this case it will be in z direction. Your direction will be constant in this case, in the given case, in the given situation. This is the given situation. So this is the concept what I want to tell you. This is the concept, and the direction of V must be, that is screw rule, nothing but screw rule, omega cross r. So because it is a cross product, so it will be perpendicular to plane containing omega and r. And what is the main important? Omega r perpendicular, omega into r perpendicular. This is the magnitude of V. This is the magnitude. So this is all about your rigid body. Now the concept is a non-conducting sphere. A non-conducting sphere of radius r is uniformly charged. That means a non-conducting sphere of radius r is uniformly charged. This is the sphere, and this is the sphere. It is a non-conducting sphere, that means insulator. That means it is insulator and is uniformly charged. Say it is, this sphere is uniformly charged. That means the surface is uniformly charged. The sphere surface is uniformly charged. The whole sphere surface is uniformly charged. Now we have to find out the variation of this is radius r. So now we have to find out the variation of electric field. That is, electric field is 1 by 4 pi epsilon naught q by r square. Variation of this electric field with radius r, that is radius r. We have to find out the variation of electric field with radius r. The graph obtained is like this. The graph we get, this is r is equal to here. The electric field increases proportionally up to r, then it decreases this. When at this portion, this is electric field, and here this is radius. So here at this point electric field is proportional to r, and it is maximum at the surface, and then the electric field decreases 1 by r square. So now what is the concept? The concept is that this is a solid sphere. So in your mind, how can there be an electric field inside the sphere? Because it is a solid sphere. So, and at the same non-conducting means it is an insulator. So the variation is this. This is the variation, that is 0. This is electric field. this is 0, this is electric field. That means from the center of the sphere your electric field is proportional to r, and it is maximum at the surface, and then it decreases, electric field decreases 1 by r square. So what is the concept here is that what is the concept here is that you may feel that how can there be a charge inside a solid sphere? So this is possible because it is a non-conducting, so it is an insulator. So you think of dielectric material. They are also insulator. But they get polarized. What is? They get polarized. That means due to the surface charge, the inside molecules, due to here plus, so the negative charge will slightly shift towards the positive charge, and towards the positive charge from the nucleus. So this will happen like this, something like this. So the charge on the surface that will polarize the internal sphere, that means this charge will pull the negative electrons towards the positive charge. So the electrons are slightly moved towards the positive charge, and as a result here the atoms gets polarized. That means plus and minus and plus charge is developed. So this is the concept. So that is the inside the sphere an electric field is developed. So inside the sphere an electric field is developed. So this is the concept. So I am taking only the particular point, that is for concept as non-conducting sphere. This is the graph, but the concept is that you may feel that how can there be a electric field inside a solid sphere. So this is possible. You think of dielectric material, and this dielectric materials get polarized in a capacitor because of get polarized. So in the same way the inside of the sphere it gets polarized. So this is the concept. Next concept is that magnetic field outside a current carrying wire. So this is the cross-sectional view. That means I current is flowing through it. This is the cross section. This is the surface of the conductor. This is the surface of the conductor. This is the cross sectional view, and we want to find a magnetic field somewhere here. Suppose at point P, we want to find the magnetic field somewhere here. So what is the concept? That we draw an Amperian loop. We draw a circular Amperian loop here, and now it is at a distance r. So from Ampere circuitry law we get that cyclic integral of B dot dl is equal to nu naught I enclosed. So this is the theory, Ampere circuitry law. So here you find that this is cyclic integral b dot dl cos theta. So now that is equal to mu naught I. The current enclosed is I. Now this is your, let us take this small element dl and a small element dl. So the magnetic field here will be, this is your direction of the magnetic field. Similarly, direction of the dl will be also, this will be the same direction of dl. That means if you hold this thumb like this, current is flowing in this direction. So the curled finger will give you the direction of the magnetic field. Curled finger. So here that is tangent at point B, at point P, that is the tangent at point P will give you the direction of the magnetic field, that is B, it is the direction of the magnetic field, and the direction of dl is also the same. So your cos theta is your 0, so your theta is 0. Here you see that your theta is 0. So now this will be cyclic integral b dl is equal to mu naught I. This will be mu naught I. So here again you see that this will be how much b dl mu naught I. So dl for the whole this magnetic field, for this whole loop, that is circumference, cyclic integral of dl, that will be circumference p into 2 pi r, that is mu naught I. So b will be mu naught by 2 pi r I. This will be your magnetic field at this point. So the same magnetic field at every point you will find this, the same magnetic field will be at every point on this circular loop. So this is how we find the magnetic field outside a current carrying wire. So here the concept here is that, see, this is the cross sectional area, that means this is the conductor, surface of the conductor, and we want to find the, here this is the P. At point P we want to, this is the length element dl, and we want to find out the this at point P what is the magnetic field. So your direction, this from the thumb rule, this is the current direction, so this is your current direction, so curled finger, so this will be the direction of the magnetic field, this will be the direction of the magnetic field. That means the magnetic field at point P will be tangential. We will draw by the, will be given by the tangent, that is tangential. So this is the concept of the direction of the magnetic field. So here the magnetic field at point P is this much, and since dl and b are in the same direction, your theta will be 0. So when your theta is 0, that is your when your theta is 0, so this will be dl, that is 2 pi r. So this is the magnetic field outside a current carrying wire. Now next is that magnetic field inside a long inside a you can say straight conductor. What is the magnetic field inside a straight conductor? That means inside a conductor. So here you see that this is the surface of the conductor of radius r, and we have to find out what will be the magnetic field at a distance r inside the conductor. We have to find out the magnetic field inside the conductor at a distance r. This is your surface of the wire. This is your surface of the wire. So here again, this is your ampere loop. Here again B into 2 pi r, that is nu naught, current enclosed. So your current enclosed will be pi r square I into pi r square by pi capital R square. This will be your current enclosed here. So this is the conductor where current is flowing through the conductor, and now this is a straight wire. Straight conductor means it is a wire, say it will be a wire. So here this will be B into 2 pi r nu naught pi r square by pi r square. So this will be B is equal to pi cancels out, r cancels out. So this will be nu naught r by 2 pi r square. So this will be your magnetic field at the distance r from the center of the conductor. So this is the magnetic field inside a straight conductor, that means wire. Now solenoid. Here you see that solenoid concept. I am dealing with only the concept solenoid. So here, like capacitance, like a capacitor in a parallel plate capacitor, you know that electric field outside the capacitor is 0. Electric field outside the capacitor is 0. Similarly, in a solenoid, your magnetic field outside the coil is ideally it is 0. Ideally it is 0. It is very less, your magnetic field is very less, so you can say ideally it is 0 magnetic field outside the solenoid. Only the magnetic field will be inside the coil. And how will you determine the direction of the magnetic field? You take your right hand, curl your fingers, when you curl your fingers, the curl will give the direction of the current in which it is flowing in the coil, and the thumb will give you the direction of the magnetic field. So the concept here is a simple concept. In a solenoid, it is like in capacitor, in parallel plate capacitor, electric field outside the plate is 0. Similarly, in solenoid, outside this solenoid, your magnetic field is ideally 0. It is very less, so it is ideally 0. only the magnetic field is inside the solenoid, and the direction of the magnetic field is given by your thumb rule. That is, your curled finger will give the direction of the current, that is the current it is moving, the curled finger, and the thumb will give you the direction of the magnetic field. So this is the concept. That is, magnetic field outside the solenoid is 0, and only it is inside the coil when current flows through it. So one more thing I left here is that I discussed about a non-conducting sphere. I discussed about a non-conducting sphere. I discussed about non-conducting sphere. A non-conducting sphere. That means an insulator of radius r and uniformly charged. So here, and another is a conducting cell, hollow cell. That means it is a hollow cell of radius r. Here your electric field, here E is proportional to R. This is your electric field, and this is your R, and it is maximum on the surface, and after that it decreases 1 by R square. But in case of a conducting cell, here hollow cell, here this is your electric field and this is your R. So there is no electric field inside the cell. There is no electric field, only it is outside the sphere, and here your electric field varies is 1 by R square. See the concept here, because in conducting cell, which is uniformly charged, this is also uniformly charged, this is also uniformly charged, but here uniformly charged, this conducting cell, but here inside the cell there is no electric field. Only the electric field is outside the sphere. But in case of a non-conducting sphere, your electric field is inside the sphere, and it is proportional to R and inversely proportional to 1 by R square. So this is the concept. These are all these concepts which you must remember. These are all this concept which you must remember. So similarly, and another concept, that is, these are important concepts which makes you clear to understand the subject properly.